Hello, calculus students and general seekers of truth. We will now look at the comparison of a power series and a Taylor series for the function natural log of x, both of which centered at x equals 1. So first, let's look at the power series. And we start out with the known fact that the derivative of the natural log of x is equal to 1 over x. Now, this is important because later we're going to write this as a power series and then take the antiderivative, and then we'll get back to the natural log function again. Okay, it's just like we did for the arctangent in the previous video. Now, our goal here is to try and rewrite this to look like, rewrite to resemble something like 1 over 1 minus r. Okay, because this is the sum of a geometric series, and this can be expanded easily to 1 plus r squared, so on. Okay, so we want to find some way to rewrite this function 1 over x to look and resemble the power series form of this. And it's not terribly difficult. We can just write it this way: 1 over 1 minus quantity 1 minus x. Okay. So if we were to work out all the algebra here in the denominator, we would get the exact same thing as this, and this is sort of our r. So we have that r is equal to 1 minus x. Now, because the question asked for this to be centered at x equals 1, we want it to look something like, x minus 1 instead, because this is more correct with the specific problem which says centered at x equals 1. This is also correct, but we wanted to, answer the question that's being asked of us. So it's not too difficult. We can just rewrite this as negative quantity x minus 1. Okay, so just factoring out a negative 1 out of that. And so now 1 over x is really equal to the power series representation. Let me write this whole thing out. Is equal to 1 over 1 minus quantity 1 minus x, which is really equal to 1 over 1 minus negative x minus 1. Okay, so this whole thing here is our r, and now it allows us to expand this fairly quickly. So this is equal to 1 plus r and negative x minus 1 is equal to r plus r squared, and once we square this, the negative sign goes away, plus r to the third and this will go on to infinity. And we can even put this all together into our sum as the summation from 0 to infinity of negative x minus 1 to the nth. So however you want to resemble it, either in the expanded form with the ... onwards to infinity, I'm missing a plus sign there, or in the summation, that's perfectly fine as well. Now, we're not quite done yet, because what we found here is the derivative of the natural log. So if we want to find the natural log function, then we need to take the antiderivative, and we're going to do this term by term. So the natural log function is equal to the antiderivative of the derivative of the natural log with respect to x, which is equal to the antiderivative of 1 over x dx, which is equal to the antiderivative of our series. So on. There should be a dx in here somewhere. Okay? I mean, all of this is multiplied by dx. Okay. Alrighty, and and I'm just writing this out, just being super lengthy here so you can see the equality. We could have just simply jumped to the end here and started taking the antiderivatives, and we would have been just fine. Okay, so the antiderivative of 1 is nothing more than x. The antiderivative of this term is negative x minus 1 squared over 2 plus x minus 1 to the third over 3 minus x minus 1 to the fourth over 4, and so on. And we know for a fact that there is also a constant in the front here, because this is an indefinite integral, so there should be a constant there. So we know that the natural log function as a power series is equal to all of this right here, and now we need to solve for c. Okay. One thing we do know for sure about the natural log function is that the natural log of 1 is exactly equal to 0. So if you pass in 1 here for x, you get 0 on the left side. On the right side, you get c plus 1 for x. And then you get zeros for everything else. And so solving this out, we get that c is equal to negative 1. Okay. So the natural log function is x minus 1. And so I'm taking this x here and the negative 1 for c and just grouping them together. And then minus all of that. Minus x minus 1 squared over 2 plus x minus 1 cubed over 3 minus quantity x minus 1 to the fourth over 4 onwards to infinity. Whoops, writing off the screen here. And we could capture all of that in a couple different ways. We could just simply say that, how do I want to write this? I think this way would be best. From n equals 0 to infinity of, I'm going to do the negative 1 to the nth, because I know this is going to alternate positive and negative signs. And then quantity x minus 1 to the n plus 1 all over n plus 1. So that sums it up for the natural log function of the power series of a natural log function centered at x equals 1. Now we are going to figure out what this looks like for a Taylor series of the natural log function. Okay, so I've started with the natural log function f of x, and when x is equal to 1, the natural log of 1 is 0. Take the derivative of that, which is 1 over x, or x to the negative first. At 1, that's equal to 1. The derivative of that is negative x to the negative second. At 1, this is equal to negative 1. And then the third derivative is positive 2x to the negative third. At 1, this is equal to 2. And we can take one more. The fourth derivative is, I'm going to write it this way, negative 3 times 2 times x to the negative fourth. And when x is equal to 1, we get negative 6. Okay? So in general, the nth derivative of the natural log function is negative 1, and it's alternating signs, so it's raised to the n plus 1 power. The reason for the n plus 1 is actually all of the odd derivatives are positive, so we need to adjust for that with the n plus 1. And if you notice here, this is nothing more than a factorial function, but it's 1 less than the derivative, so this is n minus 1 factorial times x to the negative nth. Or another way we can write it is negative 1 to the nth plus 1 over, times n minus 1 factorial over x to the nth. And at x equals 1, this bottom part here goes away because x is just equal to 1. We get negative 1 to the nth plus 1 times n minus 1 factorial. So that's the just figuring out a pattern for the derivatives of the natural log function. Now what we should look at is the Taylor series for this. So the Taylor series is, again, the sum from n equals 0 to infinity of the nth derivative at 1 in this case, times x minus 1 to the nth power all over n factorial. Now let's substitute in this part. Okay, this right here is the same as this. Alright, so this is a pattern for the nth derivative of the natural log function at x equals 1. So if we make that substitution, well, let's see what we have. We have negative 1 to the nth plus 1 power times n minus 1 factorial times this part right here, x minus 1 to the nth all over n factorial. And there's some simplifying that can be done here. N minus 1 factorial and n factorial simply reduce, okay, to n in the denominator here. So this all is equal to n equals 0 to infinity of negative 1 to the n plus 1 times x minus 1 to the nth all over n. Now this is almost done. This is almost complete, except for one little thing. I don't know if you caught it, but the starting point here is quite significant because we're saying that we started at n equals 0. Okay? Now think about what that means here. If you put 0 into this, you get negative 1 factorial, which doesn't make any sense. Okay? So we have to go back and rework this series just a little bit, and we have to say that this only applies when n is greater than or equal to 1. Okay? If it is not, if n is equal to 0, in other words, the 0th derivative, we already know we get 0. This only works when n is equal to 1. So we have to change our Taylor series a little bit here to say that this only applies when n is equal to 1. It doesn't work when n is equal to 0. When n is equal to 0, it's a special case. In other words, we get 0 anyways. Okay, so this is really like 0 plus all of this. This is the Taylor series here is really 0 plus all of this. Okay, so if I wanted to adjust this, so if I want to adjust for n equals 0, it's really not hard. All I have to do is add 1 to everything. So if I wanted to adjust for this, for n to start out at n equals 0, I could also say that this is that negative 1 to the n plus 2 x minus 1 to the n plus 1 all over n plus 1. Okay, this version up here with all the simplification, that is correct, starting at, well, I'm sorry, this is not correct. This one is correct. If we start out at n equals 1, that expression is very much true. And the main reason, again, is this n minus 1 factorial idea doesn't really work if you have a 0 in there. Now, if you want to adjust for 0, then you have to add 1 to everything up here. And you'll see that this version and this version are exactly the same. You can also see the problem before. If we had n equals 0 here, the very first thing you do is you divide by 0. So you have to adjust for this. Now, this looks very familiar, and you really should compare it to the previous series for the natural log function and see how that matches up. And then we will talk about the relationship between Taylor, Maclaurin, and power series in our little class discussion. Okay. One more thing that I should bring up here that I haven't done yet is to find the interval of convergence. Okay. And I will leave that to you. This is some good practice, and this one isn't too hard to find for either the Taylor series or the power series. Okay, so thank you for watching, and have a wonderful day.